one of the most important criteria that when we deal with the drying process is actually known as the drying curve. So drying curve is actually a plot of free moisture content. Okay, so from this point on, most of our discussion will involve free moisture content, not total moisture content. So it is a plot of a free moisture content versus time that is needed for the drying process. So basically this is an ideal drying curve where you have your y-axis as the free moisture content, and it is, you can see also here the unit here, kg of H2O per kg of dry solid, and the time. So the time actually can be in hours, minutes, or seconds depending on your material that you are drying. So if you see here, you have a few important points here: A prime to B, B to C, C to D, and D to E. So we can say that E here is your final moisture content for your drying process. So it is important for you to understand each of these lines. What is happening here? So if I were to ask you, draw or plot a free moisture content versus time, and then explain each and every segment of the plot. So what is happening from A to B, what is happening from B to C, what is happening from C to D, and then D to E. So the explanation for A to B is saying that when we have A to B, wet solid is actually being preheated. Moisture content is evaporating at an increasing rate. So this is what we can say from A to B here, is saying that it is actually our preheating process. So this is where you start. So when you start here, you will have temperature is not steady yet, your humidity is not steady yet. So this is what we call a preheat condition. So once you reach to B, B is actually known as the drying rate becomes constant. So why do I say that drying rate become constant? So if let's say we would just focus on B to C, okay, we ignore every part else, we ignore all these things, we just take B to C. So the reason why we say B to C is a constant condition, drying rate is constant, because you can say that in ideal condition, this is going to be actually a straight line. So this is going to be a straight line. So B to C. So when we have a straight line, what means that is that if let's say I want to find a gradient at this point, gradient at this point, or gradient at this point, or gradient at this point, the value is going to be the same. Doesn't matter whatever point I take along the straight line, the gradient is going to be the same. So that's why we say that at B to C, the drying rate becomes constant. So why do the drying rate become constant? So if, for example, we take this as an example of our drying material, so the drying becomes constant because during initial drying from B to C, the rate of drying is actually controlled by external mass and heat transfer between the exposed surface. Meaning that here, you will have your heated air, right, at temperature something, at humidity, some humidity, will be passing through your wet solid. So what it means that you will have a layer of water, a film of water here on top. Okay, so we are saying that your moisture is actually on the surface of your material. So meaning that the amount of water that is being removed and then transferred to your hot air is actually the same from, let's say here, maybe we can say here time 1, maybe around there, 1 until 4, right? So from here until here, the amount of water that will be transferred from your, mostly will be on your surface to the hot air, is the same amount. Doesn't matter it is at 1 hour, 2 hour, 3 hour until 4 hours. So after until 4 hours, we can say that there is no longer any water on the surface. So at point C here is the end of your constant drying rate. And this point is actually very important because this is the point your X at point C here, we can say it as XC here, is known as the point where the constant rate is ending or terminates. And this point is actually known as your critical moisture content. So when we define critical moisture content, we say that critical moisture content is where your constant drying rate ends and when your falling rate begins. And we can also say that at your critical moisture content, almost all the water on the surface is actually being removed into the air. So when we come to point C and D, so now we are focused on point C to D. At point C to D, the surface tend to be dry. Okay, no, we don't have any more moisture or water film on the surface. The rate of liquid travel by diffusion or capillary action to the exposed surface. So if you see here, now if I were to say, because this is a curve, right, if you look at here, this is a curve. So I can say here, at this point, the gradient will be different from this point and different from this point. So why is it different? Because now your heated air, the amount of water that is being transferred to your heated air is actually changing. Why? Because the rate of liquid now is based on the diffusion. So what will happen now is that the exposed surface temperature remains at the wet bulb temperature. The rate of drying decreases linearly with decreasing average moisture content. So from C to D is actually known as the first falling rate drying period. Meaning that the water first, if let's say you have your water, this is your surface. So water first have to diffuse to the surface, and then from the surface it will be diffused or transferred into your hot air. So that is why we say that the rate is actually based on the diffusion and the capillary exchange. So meaning that the longer you go, the deeper you go, the smaller the rate will become. And then we come to the point from D to E. So the evaporation or drying process occurs from liquid surface in the pore. So and the wet bulb is the prevail. Temperature of the exposed surface of the solid rises approaching the dry bulb temperature of the gas. And this is what we call as our second falling rate drying period. So the rate of drying period is actually controlled by the vapor diffusion. So again here, your liquid will have to be diffused, become vapor, and then the vapor will actually be transferred into the heated air. So the rate falls exponentially with the decreasing in moisture content. So you can see here, this is an exponential decrease in your rate. So if let's say you were asked, so you can say that here, in your constant drying rate, the drying is actually controlled by external mass and heat transfer. Okay, when we have your first falling rate, it is actually controlled by the diffusion and capillary action. When you have your second drying rate, it is actually controlled by the vapor diffusion. So because of the difference in your separation or transfer mechanism, you will have this drying curve. And from this drying curve, we can actually plot another curve or another graph known as your rate of drying curve. So whatever we have here, whatever information we have here, we translate it into your rate of drying curve. So in your rate of drying curve, we still have the same symbol that we are using. We have A prime, B, and B to C, C to D, and D to E. Now the rate here can actually be calculated using this equation. R is your rate, is actually equal to, again here, we have this negative sign. Why do we have negative sign? It's the same in our Fick's law and it's the same in our Wheeler's law. So because why? Our dx here is between, so we can see here that x2 minus x1, right? This is how dx is going to be if we, let's say, we integrate this equation, and the value of x2 is smaller than your x1. That's why we have this negative sign here. So negative ms is your mass of bone dry solid, meaning that bone dry meaning there is no moisture in your solid. A is the surface area of the drying process or the drying area. Dx is the difference in moisture content, and dt here is the change in time. So when we want to plot here, so that's why we can say that when we have your point A to B, since it is a constant drying rate, that's why we have a straight line. So if you remember, I said that, let's say we draw it again here, A to B, oh no, B to C, sorry, B to C. If let's say we find the gradient, it will give me the same value. So this is the gradient that we are talking about. So this is actually why we get a straight point for your B to C point. And when we are talking about point C to D, we'll have a straight, kind of a straight line, and sometimes we can have a slope, because now the gradient and the value of R is actually changing, because it is actually depending on the diffusion and capillary action. And when it comes to D to E, since it is controlled by the vapor diffusion, so you will have another different curve. And again here, we have actually labeled here, XC is our critical moisture content. So you must be able to actually convert your drying curve into your rate of drying curve. And you must be able to understand what is the connection between your drying curve and your rate of drying curve. Okay, the drying process is actually divided into two major parts, right? We have the constant rate period, mentioned just now, from B to C, and also falling rate period. C to D is your first falling rate period, and D to E is your second falling rate period. And when the constant rate period ends and the falling rate period starts, the critical moisture contents, the moisture content is known as your critical moisture content. So your XC here is known as your critical moisture content.